a little bit.
Yeah.
I'm sure like you should spend most of the time with students.
Yeah. Oh, we can also catch up later and stuff. Yeah.
Okay, let's start. So let me just first introduce our new lecturer, Safdi. So Safdi is a professor at Berkeley. So actually, Ben has a treaty on Europe with career trajectory. So I'll say a few words. So Ben started in graduate school. He's actually a formal high-energy theorist. So he's working with his advisor is Igor Klebanov, a prominent like string theorist, formal high-energy theorist.
Earlier, he was an undergraduate here.
Then he studied like a PhD working on, like say, formal topics like RG flows of three-dimensional field theory. Then in the later part of his PhD, he RG flowed himself to a completely new territory. Now he found his new fixed point of dark matter research. And he stays at his new fixed point after. So Ben actually has proposed a novel like lab research for dark matter in like abracadabra, and he's also applying data-driven approaches to look for signals of dark matter in astrophysical data sets. So this is actually the subject he will lecture on. So without further ado, let's move on.
Thanks. Can everyone hear me okay? Awesome. So yeah, it's great to be here. See everyone in person. I actually never got the pleasure of going to Tazi when I was a student. So I've heard so much about it, and it's nice to actually be here and see it for myself. So today and this week, I'm going to be talking about dark matter, and in particular on astrophysical probes. And I hope that this is complementary to your many other lectures on various other aspects of dark matter. I think there's going to necessarily be a little bit of overlap here and there. So if you find yourself just snoozing away, saying, just let me know that you've already seen it, and I can kind of skip over something as we go. So let me tell you an outline of what I plan to cover. So today, I'm going to be giving you kind of a rapid dark matter overview, but focused on astrophysical probes in particular, as opposed to, for example, models. And then if I have time, I'm going to start talking about annihilation and decay and specific dark matter models. Then days 2 and 3 are going to really be focused on annihilation and decay. And then day 4 will be axions. And I think you've already heard a little bit about axions from Peter, for example. But when I'm doing axions, I'm going to be focusing mostly on how you can look for them in astrophysics. So the theme of all of these different days is going to be astrophysical probes of dark matter. And in addition to this, I have a homework question, which I put on the Google Drive. Did anyone notice this by chance? Awesome. So I put a Jupyter notebook on the Google Drive that you can load using, I forget what it's called, but it's Google's kind of virtual server. Collab, Google Collab. So, so this is this Jupiter example. And I think maybe the most important thing I can provide to you is not the lectures, but is this example. This example is meant to empower you to do similar such research projects in the future. So what this example is, just to say a few words, so this relates to something called the Fermi galactic center excess, which maybe some people have heard of, maybe not. I'll explain it to you if not. This is an excess of gamma rays which has been observed around the galactic center, which could be due to annihilating dark matter. So as we'll explain throughout these kind of first 3 days, if dark matter is annihilating in the galactic center, it would also be annihilating elsewhere in the universe, including in dwarf galaxies, which are subhalos of the Milky Way. And in this example, you're going to look at data up through last week when I pulled the data from the Fermi telescope towards a dwarf galaxy. And your goal is to see if that data is consistent or not with the galactic center excess. And the exciting thing is that no one has done this. The last time this exercise was done was 2015. The size of the Fermi data set has doubled since then. And I just pulled the data and I stuck it in there and I didn't analyze it. So I have absolutely no idea what the answer is. So it's possible that in doing this problem here, you will discover dark matter. That is a possibility. I don't know. I didn't look at it. So go through that exercise, make the plots. And in the process of going through that exercise, you're going to get familiar with statistics and just understand how all of this stuff works in practice. And I think that's really useful because astrophysical probes of dark matter are really powerful, but it's also a really good place to kind of jump in as a young researcher and make progress. And the reason is, at least this is how I found kind of my career trajectory, it is hard to just sit down and think of a model. Like, I mean, you need to ask, like, what is the +1 of yourself? And maybe you're super smart and you can just sit down and think of some new model. That's not how I am. But with astrophysical probes of dark matter, what are you taking advantage of? Why now? You're taking advantage of data. And you're taking advantage of the fact that most people are really scared by data. But it's actually not that bad. So if you are willing to, there are so many kind of really important and powerful projects that you can do by just going out and thinking about data in the astrophysical realm and how to connect the data with dark matter. So I hope to give you some flavor of that this week to empower you to go out and do this in your own careers. Okay, so let's start talking about dark matter. So dark matter, we know it exists. You've heard this many times, I'm sure. There's about 5 times more dark matter than ordinary matter out there in our universe, blah, blah, blah. OK, but the thing that we don't know about dark matter is what it's like at a microscopic level. And that's going to be the question. That's the question, essentially, of all of your lectures here on dark matter. And that's going to be, in particular, the question that's going to be kind of motivating these lectures today. So when we start talking about particle dark matter, this one moves. Yeah. It's pretty amazing how little we know. So if you focus on one aspect of the dark matter, which is the mass of the particle, then from a particle perspective, the mass of the dark matter could be so low that it's like 10 to the minus 22 electron volts, and it could go all the way up to the Planck scale, and it could go up even farther if you're allowing yourself to talk about, say, composite dark matter like black holes. And you're going to be having lectures on black holes starting, I think, this afternoon, so you'll be hearing about that. So this lower mass here, 10 to the minus 22 eV, this roughly comes from the fact that at these low of masses, the quantum wavelength of the dark matter becomes galactic scale. So more precisely, you have the uncertainty relation, delta x dot delta p is about h bar. And so what this tells you is that delta x, it can't be smaller than h bar over delta p, which is m times v. So if you look, for example, at a dwarf galaxy, which we'll talk more about, dwarf galaxies have velocity dispersions on the order of about 20 kilometers per second. And their sizes are on the order of kiloparsec. And so if you solve this, you'll find that the mass that sets these two things equal to each other is about 10 to the minus 22 electron volts. So if dark matter had a mass smaller than this, there would be a sort of quantum pressure that would modify the structure of dark matter on scales at which we measure things. Meaning that down here is forbidden, just by gravity plus quantum mechanics. So nothing about the non-gravitational interactions of dark matter. Similarly, there's another bound, which is at about 100 eV, which is the Tremaine gun bound. And so the Tremaine gun bound applies to fermionic dark matter candidates. So if you're a bosonic dark matter candidate, you can live from 10 to the minus 22 eV all the way up. If you're a fermionic dark matter candidate, you need to start at about 100 eV or so. And the reason is that if you start to go below this, you end up with high occupancy numbers per each quantum state, which you're allowed to do if you're a boson, but you're not allowed to do if you're a fermion. So I'm not going to go through the Tremaine gun bound. Instead, I'm going to assign it as an exercise. So let me give you the Tremaine gun bound exercise. And I encourage everyone to go through this. So you can do a simple version of this in the following way. Imagine you have some mass, some spherical shell with mass m and radius r. Sorry, not shell. This is a solid sphere. So we're going to approximate a halo by some solid volume, total mass m, constant density, radius r. That's not how actual galaxies work, but it's fine just to get an order of magnitude. So then the exercise involves the following. Calculate the Fermi velocity that's associated with this system. And that Fermi velocity should be smaller than the escape velocity of the system. And if the Fermi velocity is larger than the escape velocity, that gives you some sort of inconsistency in that object existing, because you're going to be packing. You can't keep on adding states on top of each other, so you have to fill them out. You're going to have such a large Fermi velocity that actually particles are going to be escaping from your system. So if you go through this, you should find a mass of about 100 eV if you stick in typical dwarf galaxy parameters. So take a mass on the order of about 10 to the 7 solar masses, and take a radius on the order of about 2 kpc, 2 kiloparsec. So go through that and let me know what answer you get. Yeah? Yeah, so here, just assume you have one species of fermion, and that's it. And don't think about interactions or anything like that, just one species of fermion. Yeah. Yep.
I got a question about the fuzzy dark matter thing. I know that everyone always says 10 to the minus 22 in talks, but I've also seen papers in the archives that say 10 to the minus 21, some say 10 to the minus 20. Is there like a developing consensus about where it is?
Oh yeah, that's a super interesting question. Yeah, so 10 to the minus 22, okay, let me just give you a 2-minute aside about fuzzy dark matter, because I'm not actually going to talk about it anymore. Fuzzy dark matter is interesting. Fuzzy dark matter is dark matter which lives right around here. This is fuzzy dark matter territory. It's a great name. So fuzzy dark matter, why is it fuzzy? It's fuzzy because it has this kind of quantum poofiness to it as you try to squeeze it down on these small scales. So fuzzy dark matter is interesting for theoretical reasons and for observational reasons. Observationally, there have historically been various discrepancies on small structure. Maybe I'm going to tell you a little bit about some of those structure anomalies. So by structure, I mean subhalos. So halos with masses on the order of 10 to the 7 solar masses, 10 to the 7, 10 to the 8, 10 to the 9. And since this dark matter candidate modifies structure on those scales, it can explain some of those anomalies. And so this is motivated from kind of a data perspective, people to think about dark matter at this mass scale. Theoretically, when we get to axions, I'll talk about this. Fuzzy dark matter is an example of an axion-like particle. And these particles are motivated from, for example, string theory constructions. And it also turns out there's a natural way to get the correct abundance of dark matter, which we'll go through. So you have kind of theory converging with experiment. The problem is that now data and modeling have gotten better, and the mass limit has slowly marched upwards. I would say the consensus is certainly like 10 to the minus 21 electron volts at the moment. So really, you should be replacing this 10 to the minus 22 with 10 to the minus 21. And it might even be higher by looking at systems like the Lyman alpha forest, which I'm not going to get into because it's a bit of an aside. But there's some modeling assumptions that have to go into that. But yeah, more precisely, it's probably 10 to the minus 21. But I'm leaving it 10 to the minus 22 just for historical reasons. OK, so we're going to be focusing today and all this week on astrophysical signatures of particle dark matter models. And so there's a variety of particle dark matter models, obviously, which inhabit this entire parameter space. But almost every single one of them leaves some sort of astrophysical signature. Maybe that astrophysical signature is really hard to see. But there's typically some sort of astrophysical signature of the dark matter model, which can be used to discriminate it from other models and can be used to learn something about the particle nature of dark matter, like the mass of the candidate. So I'm going to broadly categorize the type of astrophysical signatures. Then I'm going to tell you about the types of models that we're going to look at, and I'm just going to draw some arrows between the two. So the classic astrophysical signature is cosmic ray. So cosmic rays can include gamma rays, X-rays, radio, so the entire electromagnetic spectrum, neutrinos, charged cosmic rays like E plus, E minus, and protons and antiprotons. So these are things that you build telescopes to look for. So you build a telescope, you go and you look out in the cosmos, and you say, hey, wait a minute. Dark matter isn't actually dark. It's producing a very faint amount of light or something else. And you go and look for that other thing. So types of dark matter models which do this include WEMP dark matter from annihilation and decaying dark matter from dark matter decays. An example of this would be sterile neutrinos. Also, axions can produce signatures here, for example, in the radio band. And I'll tell you about that a little bit on the last day. So in addition to this cosmic ray probes, which are kind of the classic probes of looking for particle dark matter, you also have probes of stellar evolution. So these can be, essentially, this is the idea that if you have BSM particles, they can modify stellar evolution. And the classic example of this is axions. So here, the idea is not that you're looking for the dark matter itself, but you're saying if this particle exists within the spectrum of nature, it can be emitted inside of stars. So stars 101, stars cool by emitting neutrinos from their cores and thermal radiation from their surfaces. Now, if you have other light states of matter, which often can be associated with dark matter, like dark photons or axions, they can also be emitted from that hot thermal core. And since necessarily they're weakly interacting because you want them to be dark matter, they can escape those systems and provide a new pathway by which stars can cool. So we'll go over stellar evolution a little bit in the context of axions. Then there's structure formation. So structure formation, we talked about a little bit already. But this is looking at halos, halo shapes, and numbers, essentially. And when I say halos, here I'm referring to dark matter halos, like what we live in, the Milky Way. And structure formation can be associated with, for example, sterile neutrino, dark matter, also with axions, with fuzzy dark matter, like we just discussed. Then, yeah.
I had a question about the stellar evolution.
Yeah.
So it seems surprising to me that we could put competitive bounds on dark matter based on stellar evolution, because aren't there like huge error bars in our knowledge of how stars actually work?
Yes and no. I mean, stars, we do understand how they work pretty well, but it depends on what type of star. If you talk about a neutron star, there are more uncertainties than if you're talking about our own sun, for example. As a general statement, setting limits on dark matter is hard because you always have to ask yourself about your knowledge at the limit of how well you understand something. Because if you don't see something, you want to set a limit, and that limit is going to be when that thing starts to become important. And so you're necessarily going to be trying to understand a system at the very edge of knowledge. On the other hand, at some point, you would just kill the star. So as you crank up the coupling to matter, the stars don't even exist, or they exist for like a second and they just cool down. So in practice, doing this is hard. Doing anything with astrophysical dark matter, probes of dark matter, is hard to do it precisely. Doing it not precisely is typically very easy. Because you just say, OK, first order, I want my star to still exist today. And then, that's fine. If you say, what is the 95% upper limit on the axion-photon coupling from this particular neutron star, then you spend a year trying to understand all the systematics associated with neutron stars. Yeah?
QCD aside, is the 3 arrows by axions such a buffer?
No, actually, yeah, good, sorry. The question is, are these 3 arrows the reasons why axions are popular candidates? And I'm actually going to draw a 4th arrow. So, but no, the reason that axions are popular candidates is because they're very well motivated theoretically.
Sorry, I mean for detection.
For,
Like,
yeah, all of these arrows are extremely hard.
Okay.
And so it's even though there's a lot of arrows, that's not really the driving factor, I would say, for interest in axions. The driving factor is really theoretical. Okay. It just turns out that there are various ways that we have of probing axions, but they're all extremely hard. I would say, yeah, I mean, as I mentioned, everything is kind of hard in this game at the limit, but yeah, these in particular are quite difficult. OK, just one more box here. Sorry, this is getting a little bit messy. Early universe probes. So early universe probes, I mean things that affected the universe from CMB decoupling or before. So BBN or dark matter affecting the CMB. So a classic example of an early universe probe of dark matter associated physics with dark matter would be, for example, ineffective, the effective number of neutrino degrees of freedom. And axions, again, can contribute here. And WIMP dark matter can also be detectable with probes of the early universe. So in these lectures, we're going to touch on each of these 4 categories. But we're mostly going to be focusing on 2 classes of dark matter. We're going to mostly be focusing on WIMP dark matter and on axions. And this is for a few reasons, 2 reasons, really. One, WIMP dark matter and axions, as you can tell by these arrows, they illustrate how to probe dark matter across essentially all of the different astrophysical categories that we have for probing dark matter. So for the illustrative purpose of illustrating methods, which is going to be the focus of these lectures, they're great models to illustrate. Also, though, I feel like it would be unwise for me to just tell you about every dark matter model without injecting at all my opinion of which ones are more motivated than others. And it is just my opinion that our 2 best dark matter candidates that we have at present are WIMPs and axions. So I'm going to be focusing on those for that reason, too. OK, so let's now take a step backwards and just remind ourselves about structure formation dark matter halos, this word I've been using a lot so far, and how dark matter evolved starting from after the Big Bang into the halos in the galaxies that we have today. And we need to understand this because most of the astrophysical probes that we're going to be focusing on will require us to understand the distribution of dark matter in galaxies today. So we need to understand how that kind of came to be. So let's just do a quick kind of crash course in structure formation. So after inflation, this is kind of directly after inflation ended, quantum fluctuations in the inflaton field imparted small density perturbations to matter, in particular to the dark matter, which is the dominant source of matter out there in our universe. And these perturbations are very small. Yeah?
When are you defining inflation to end?
Good. So these perturbations are generated during inflation, and they exit the horizon. Oh, sorry. The question was, when am I defining inflation to end? So these perturbations were generated during inflation. They exit the horizon. For the purpose of what I'm about to tell you about, let's assume reheating has happened and we're in a radiation-dominated universe. So we're in a radiation-dominated universe. The universe is expanding. And what happens is that as the universe expands, these modes are going to enter the horizon. So you have some mode, and it becomes comparable to the Hubble parameter. During radiation domination, still nothing much happens. This mode will slowly start to grow. But once you get to matter domination, where matter is the dominant source of energy density, then this thing really starts to self-gravitate. It's not really self-gravitating much during the radiation-dominated era, just because the universe is dominated, the energy is dominated by radiation. Once you get to matter domination, these modes start to grow. And so these start to collapse onto each other. And it's these modes which then collapse down and form dark matter halos. So these things become your dark matter halos. So as they are collapsing down, forming dark matter halos, they're pulling in ordinary matter. So let's just go through this again. After inflation, quantum fluctuations during inflation give you very small density perturbations. After inflation ends, the universe is expanding. The horizon is expanding. And as the modes enter the horizon, as these fluctuations enter the horizon, they can then collapse under their own self-gravity, specifically during matter domination. They are collapsing and they're forming dark matter halos. As they form those dark matter halos, they pull in the baryons. They pull in, so baryons, throughout all of these lectures, are just going to stand for ordinary matter. So they pull in the baryons, the ordinary matter. And so after this, today, around redshift z equals 0, you have dark matter halos. Well, actually, let me say redshift slightly more than 0, plus ordinary matter. So this stuff is the ordinary matter. But the ordinary matter, which is just a gas at this point, it's going to collapse down. Why is the ordinary matter going to collapse down? Dissipation. Ordinary matter is different from dark matter in a few crucial ways. Ordinary matter has non-gravitational interactions, and in particular, it has dissipative mechanisms. For example, where you can produce photons, you can produce radiation, and those photons are then going to escape. So you have sources of energy loss. So you can have scattering, and you can have energy loss. And so the ordinary matter, which is pulled in by the dark matter, is going to undergo scattering. It's going to undergo dissipation. It loses energy. As it loses energy, it falls. The matter is going to fall towards the center of the potential. But angular momentum is conserved. So what happens if I'm spinning and I pull my arms in? Do I go faster or slower? I go faster. So I start speeding up, and I become I flatten. Well, I don't, but a ball of dough would if you imagine like spinning dough to make pizza or something. And that's what happens. So you dissipate, you lose energy, and as you lose energy, you flatten yourself down into a pancake, and so you end up forming disk galaxies. So we have the dark matter halo, which didn't do this because the dark matter doesn't have dissipative mechanisms and self-interactions. And then you have your disk galaxy, which is going to be smaller than the dark matter halo because the dark matter halo didn't collapse down. Yeah?
Question about the dark matter collapse. I would naively expect that you dilute the dark matter so much that it wouldn't collapse as the universe expanded. Why is the dominant mechanism that you're collapsing down?
Yeah, good. So the question is that you would expect to kind of dilute the dark matter such that so that it doesn't, so that it wouldn't be able to collapse down. So good. We're going to get into how everything dilutes, but radiation dilutes in some sense faster than matter, because essentially as the universe expands, the number density, regardless of whether it's radiation or matter, is redshifting the same way. But radiation has this other funny aspect that that the energy is also redshifting, whereas matter, the energy is set by the mass. So matter is redshifting slow. The energy density is redshifting more slowly than radiation. So everything is being diluted, but matter is being diluted less slowly. So when you get into matter domination, the matter is in charge. And it is now the dominant source of energy density in our universe. And so then these perturbations, well, this is just an overdensity of matter somewhere, and a matter-dominated universe, so it's going to collapse under its own self-gravity. But then you end up into the cosmological constant, or the dark energy-dominated era, and then everything starts accelerating again. So there is a bit of a conspiracy to actually get structure to form out there in our universe. Yeah?
So thinking about the normal matter forming into these disk shape, I would assume like the dark matter halo would also want to squish from the gravity of the normal matter.
Yeah, that's a great that's a great question. So the question is, does the dark matter also squish down into disky-like shapes just because of gravity? So to leading order, the answer is no, but there's a more subtle answer. The reason is that there's more dark matter than ordinary matter. So to leading order, dark matter is in charge, and it is just setting the halo for the ordinary matter, and the ordinary matter isn't really back reacting onto it, just because there's 5 times more dark matter than ordinary matter. I mean, another way of saying this is that what are the keys to life, right? You think like water or whatever. Dark matter is one of them, because without dark matter, you never form deep enough potentials to pull in the baryons. So dark matter is playing a crucial role in forming galaxies, visible galaxies, but it's doing that just by making that potential. But there's a more subtle answer to your question, which is in the context of some n-body simulations. You do actually see exactly what you're talking about. Some fraction of the dark matter being pulled into some sort of disk and creating some kind of fluffy dark disk, which would be a subdominant fraction of the dark matter. But this does emerge in the context of some numerical simulations. And it can have important implications for direct detection experiments. Yeah?
Out of curiosity, does this at all kind of get thicker, because dark matter is in charge here in the center, you expect the disk to get thicker, and then kind of try to collapse it again. So does it either get thicker or oscillate in some weird fashion? The
disk?
Yeah.
Good. Yeah, so the question is, yeah, good. Can the thickness of the disk be affected by the dark matter halo? Let me postpone your question for just a few minutes, because I'm going to talk in a minute or two about the interplay of baryons and dark matter in the context of n-body simulations with baryons. Yeah?
Quick clarifying question about the timeline. So at matter radiation equality, these dark matter halos start collapsing. You mentioned that the baryons kind of get pulled in with them. But matter radiation equality is before recombination. So do the baryons actually fall in at that time, or do they have to wait until after they're uncoupled from the proton?
Good. So that's a great question. They start falling in, but at this point you have this fluid, and so what happens is you have these potential wells, and which are from the dark matter. So this is a potential well that I'm drawing here. So this is the potential. And the dark matter is forming this potential, but then you have this fluid of matter coupled to radiation, because as you mentioned, they're still connected at this point. And so as the ordinary matter is falling in, it's going to have various forces which act on it from the fact that it's this coupled fluid with the radiation. So the ordinary matter is going to come in, and you can think of it as falling in, but then it hits like some spring. You can imagine there's like two balls falling into this potential well, and there's a spring between them. So you can't compress this fluid down just forever, and then it's going to bounce back. And as it bounces back, it creates these acoustic modes, which you see in the CMB. So the cosmic microwave background, you know, all those little fluctuations, those are literally the modes of the ordinary matter bouncing back and forth in the context of these potential wells. Yeah?
Do we know that throughout the age of the universe, we always have like dark matter domination? Like, what if you have a freezing scenario? Then how would this like change?
Yeah, so I'll sketch the energy. Oh, good. So the question was, do we know that dark matter was always kind of dominating the energy? Is that the question? And the answer is actually we know it wasn't. So the universe was radiation dominated before it became matter dominated. So I'll sketch that in a little bit, kind of the.
As in like between dark matter and ordinary matter.
So from matter radiation equality until the universe became dominated by a cosmological constant, yeah, we know pretty well that the universe was dark matter dominated. I mean, there's some wiggle room for kind of late decaying subdominant species of dark matter, but at an order 1 level, yes. From that point on, we have precision probes of structure formation which point us to the universe being matter dominated. Before that, that's right. Before that matter radiation equality, even a little bit before that from precision probes with the CMB, Lyman alpha, and such things. Yeah. Yeah.
Are we going to talk about the CMB power spectrum in detail?
We are not, because Dan Green will.
Okay. Can I ask just a quick question?
Yeah.
So related to that, I've heard it said that one of the peaks in particular tells you about the dark matter of the Baryonic oscillation, talking about the dark matter, like, I don't know, density. Which one is it?
Yeah, so all of the heights of all of the peaks kind of are adjusted by the dark matter and then the dark matter to baryon ratio. I am going to postpone any questions about the CMB power spectrum to Dan, because he's going to do this in detail. So he's going to go through all these different peaks and what they tell you about everything, and I would do less of a good job than he will. So save your CMB questions to him. We've been coordinating on this, so he should pick up where I'm leaving things off. Okay, so this picture is well, it's not completely correct for a few reasons, but we're going to get into what those reasons are. But let me just mention kind of real fast that already just from this picture, you can constrain different dark matter models. So there are models called warm dark matter models. Sterile neutrino dark matter is an example of a warm dark matter model. And in warm dark matter models, dark matter is warm. What's warm mean? It means it has some velocity. The dark matter particles are not just sitting here stationary, but they're moving. And they're moving with very small velocities. And what this is going to do is it's going to wash out structure on the smallest scales. And so warm dark matter can be constrained by looking for halos on smaller scales. So different particle dark matter models, fuzzy dark matter included, warm dark matter, self-interacting dark matter, they modify structure on the smallest spatial scales, and they can be searched for and constrained by looking for modifications to structure. Yeah?
Has there been a study of the effects of neutrino decoupling on the smaller structure, just from gravitational drag?
So neutrino decoupling happens pretty early on in the universe, but at scales, yeah, where we can't really probe things. But neutrinos, ineffective, which I mentioned, those relic neutrinos, which are still around at CMB times, do affect the CMB power spectrum. They do affect large-scale structure. And yes, that is a huge study because, as we'll mention, there are BSM models like axions, which can modify the effective number of neutrinos, and those can have important, those can be searched for with CMB and large-scale structure data. Yeah?
Thanks. How could you have a Friesen model that's not totally ruled out by this story?
Oh, the dark matter needs to just freeze in earlier. So it needs to freeze in before matter radiation equality or before that. Okay. So yeah, but dark matter needs to be behaving like dark matter, at least from matter radiation equality, but actually from a little bit before.
Okay. But pre-CMB, you're pretty free to.
You're pretty free to start to dark matter is a subdominant component of the energy density, so you're pretty free to kind of do what you want. As you approach matter radiation equality, you can start to see the dark matter. So then you have to be a little bit more careful. Yep. So, OK. Let's talk about making this picture a little bit more precise. So more precisely, you have hierarchical mergers. So it's a very hard word to write. Hierarchical mergers. So this is the idea that you have this spectrum of density perturbations, which I'm exaggerating here. And the smallest ones are going to collapse first. Why do the smallest ones collapse first? So this becomes a halo. Because Hubble, the cosmological horizon is expanding. And as a mode falls in, it can start to collapse gravitationally. So the smaller modes are going to collapse first. So all of these really small peaks start to collapse into halos. This forms a dark matter halo. And this will form a dark matter halo. And this will form a halo. But then these halos can merge together. And these halos will be representative of the overdensity on a larger scale. So then these collapse down to form a bigger halo. And eventually, collapse down with that one to form an even bigger halo. So you start forming structure on very small scales, but then all of those halos merge together to build up bigger and bigger halos. Yeah?
Will they get sufficient density to get black hole formation from dark matter?
Good. So the question is, can you get to sufficient density to form black holes? And the short answer is no, at least not without new physics in the dark sector. And just from lambda CDM alone, which is what I'm describing here, this hierarchical merger scenario here actually limits the densities to be relatively modest. So because every time you merge with something else, it becomes slightly less dense. And so the dark matter halos that you end up with are kind of fluffy things. They're not super extreme environments where you're going to be forming black holes. Yeah?
Is all of this known by probing substructures, like the time it collapses?
Yeah, so this is all known at a precise level down to some spatial scale by large-scale structure data, by the CMB, and then by literally just counting up halos. And by measuring halo shapes, which is what I want to mention now. So when you go through this exercise, what you find is that you tend to form what is called the NFW profile. So the NFW profile is a dark matter profile within halos which emerges in the context of dark matter only in-body simulations. So what is a dark matter only in-body simulation? You take this initial spectrum of density perturbations as predicted from inflation. You discretize it into particles. You add in the radiation component of the universe, and then you solve Einstein's equations, and you watch these densities collapse down into halos. You watch those halos merge together to form bigger halos. You just watch this whole scenario that I'm describing take place. Then, at the very end, you end up with dark matter halos. And those dark matter halos, you can then measure the density profile. There's going to be more dark matter towards the center of the objects, and there's going to be less dark matter as you go away. What do I mean by a dark matter only in-body simulation. I mean, you don't include baryons, because baryons are a subdominant contribution to the energy density. As I said, they're just spectators in this whole business to first approximation. So you ignore the baryons completely, and you just form the dark matter halos. So the NFW profile looks something like this. So what you find are roughly spherically symmetric halos. So this picture that I'm drawing over here of this kind of circle, this is roughly right from what you find from in-body simulations. It's roughly just a spherical blob. And as a function of distance, the dark matter profile increases as you go towards the center, which is what you'd expect, because these things are collapsing down onto each other. So let me just put a few scales here and write the equation. And I'll stop for the questions. So there's a kind of a crucial scale, which is the scale radius. And at the scale radius, the density profile is roughly going like 1 over r squared. At larger radii, the density profile is going like 1 over r cubed. And at small radii, the density profile is going like 1 over r. So I'm going to write down the formula for the NFW profile, but this is actually the important thing to remember, not the formula itself. The scale radius roughly sets where the density profile changes from 1 over r to 1 over r cubed. It kind of needs to be going like something like 1 over r cubed because you want to have a finite amount of mass. So if it was going like 1 over r squared out to infinity, you would have a divergent total mass. It's still logarithmically divergent, but that's fine because the density profile should eventually just connect with kind of the average dark matter density out there in our universe. So let me just write down the equation. So rho of r, this is spherically symmetric. R is the spherical r is rho 0 r over rs, the scale radius, and then 1 plus r over rs squared. Yeah, so questions? Yeah, in the back.
I just wanted to ask, you said this comes from in-body simulations. Is there like
Yes, I will mention some of next. Yes. Oh, good. The question was, is there experimental evidence? And the answer is yes, tons. And I'll mention one piece. Yeah.
How is this picture compatible with fuzzy dark matter?
Good. So fuzzy dark matter how is this compatible with fuzzy dark matter? Fuzzy dark matter would modify the halo shapes at the smaller scales, which are more noticeable when you're talking about a small scale halo, like a subhalo. So fuzzy dark matter could do various things. It can change the halo shapes. It can also make that halo more easily disrupted, or it can mean that halo would never actually form because this overdensity could never collapse in the first place. Yeah?
What will be the smallest halo?
Yeah, what's the smallest halo? Great question. The halos could be incredibly small. The smallest ones we observe have masses on the order of about 10 to the 7 solar masses. And 10 to the 7 solar mass halos, I'm going to talk more about baryons in a second, but 10 to the 7 solar mass halos have maybe, some of them have like 1,000 stars in them, or less, hundreds of stars. So they're ultra faint. There's actually a thing called ultra faint dwarfs, which are the smallest subhalos that we see. So as you go to smaller and smaller halo masses, there are fewer and fewer stars. There's already less ordinary matter than dark matter anyways. But when you have a smaller halo, it's harder for it to really compete with its neighbors and pull in lots of baryons. So when you get below about 10 to the 7 solar masses, it's actually expected that those halos are, to first approximation, dark. They haven't actually been able to pull enough baryons to form stars. So if you want to go look for like a 10 to 5, 10 to 4 solar mass dark matter subhalo, you can't go look for them with visible light from stars because they didn't pull enough baryons to form stars. So you can try to look at their gravitational lensing signatures, but even that's hard because 10 to the 4 solar masses is not that much. These things aren't that compact. So it becomes hard to actually look for them. But in the context of specific dark matter models, you can answer this question. So for example, in WIMP dark matter, the subhalos could be as small as 10 to the minus 9 solar masses, which is tiny. And that actually could be important because maybe I'll mention this later, but these subhalos, substructure can boost your dark matter annihilation signature. So substructure on very small scales can be important for indirect detection, even if it's not visible with our telescopes just by looking at ordinary matter. Yeah, second row.
Yeah, so when people set these astrophysical DM bounds, how do they decide to choose like between NFW, generalized NFW, INESTO, Bucker, Kirkquist, like all the other ones? Like.
Yeah, so we'll get it. Yeah, good. How do you decide on which dark matter profile to choose? Let me postpone that question until I talk about baryons. Dark matter only in-body simulations pretty robustly find NFW or modest variations to NFW. When you add in baryons, the situation changes, and I'll talk about that. And it becomes, really kind of an art plus just looking at in-body simulations. I mean, this is kind of the cutting edge. I'll kind of leave you where the cutting edge is. Yeah.
So you said for the dark matter only simulations, you get roughly spherically symmetric halos. But if your dark matter is not self-interacting and you only have dark matter, why wouldn't you get exactly spherically symmetric halos?
Well, you don't necessarily have completely spherically symmetric collapse. And you do have angular momentum conservation. So you are going to get some slight asymmetry, typically to your halos, if you look at a given in-body simulation. It's also, remember, it's the hierarchical mergers. So maybe you have one big merger, which happened to come in on the left side of your halo. And then that's going to, depending on when it merged, maybe you even still see that subhalo there in that left corner today. Yeah?
I don't know if you have percentages or any way of commenting on sensitivity to initial conditions of the simulation up here.
Yeah, so I mean, this sort of, sensitivity to initial conditions. These sorts of probes of halo shapes and structures and structure formation generally and CNB is how we measure this initial perturbation spectrum in the first place and verify cosmological models, which is part of what Dan Green is going to be talking about. So the flip side to your question is, this is how we probe perturbations of the universe at very early times. Which is not the angle that I'm getting at. The angle I'm getting at is I just want to know what these halo shapes are so we can go and look for things. But other people, like Dan, they care about this because it probes the early universe at right after inflation. Yeah?
So are these very small halos the ones that are formed very early on, but they did not find another one to merge?
Good, yes. So exactly, yeah. So the question is, are these subhalos that I'm talking about halos which merge early on but then didn't merge with another partner? And the answer is yes. So you have hierarchical structure formation, which means two halos will merge with each other, and maybe they merge and they're both disrupted. Or maybe they merge and one of them kind of hangs on and still is gravitationally bound. So substructure of the Milky Way can take on all sorts of shapes and sizes. You can have halos which merge, were completely disrupted, and are now virialized. They're just part of the smooth dark matter halo. You can have halos which merge, but they're compact enough and they stayed far enough away from the galactic center that they're still visible subhalos today. And those are dwarf galaxies. And you can have combinations. You can have halos which merged somewhat recently and then were disrupted, but you can still tell that they're a halo, leading to things called like tidal debris. So stellar streams are an example of this. Stellar streams, if you look out, you probably can't see this just with your naked eye, but if you look at pictures of the Milky Way, you can see these streams of particles, which come from recent mergers of subhalos, which were disrupted, but from phase space conservation arguments, all the stars kind of stayed in a line. And you can just see them visibly. You can see them in pictures. Yeah.
Is the NFW profile purely empirical, or is it?
Great question. Yeah, the question is the NFW purely empirical? And the answer is yes, it is purely empirical. It fits in-body simulations, but there is no derivation of the in-body profile of the NFW profile. If one of you want to derive this from first principles, that would be awesome. That's still lacking. Okay, so I'm going to talk about I'm going to talk about baryons. But before I talk about baryons, let me just mention some numbers here for the Milky Way. So the Milky Way is what we're going to be talking about most. That's our galaxy. So the Milky Way, the local dark matter density, this circle with the dot is going to stand for the sun. So when I write rho circle dot, that means the dark matter density at the location of the sun is about 0.4 GeV per centimeter cubed, which corresponds to about 0.01 solar masses per parsec cubed, depending on which units you like. This is a number, and it is just going to look like a random number to you. But it's good for this number to not look like a random number to you. So let me just quickly tell you how you could have guessed 0.01 solar masses per parsec cubed. The Milky Way has a mass of about 10 to the 12 solar masses. And the distance of us to this galactic center is about 8 kiloparsecs. And the scale radius is about 20 kiloparsecs. So there's roughly about 10 to the 11 solar masses within a box of about 10 kiloparsec cubed. So let's just imagine, there is this dark matter profile, but let's imagine it's just some constant sphere. There's about 10 to the 11 solar masses within 10 kiloparsec cubed. So 10 kiloparsec cubed is like 10 to the 12 parsecs cubed, because you take the kiloparsec to parsec, then you've got the 10. And then that's about 10 to the 11. So 10 to 11 solar masses over 10 to the 12 parsec cubed. That gives you like 0.1 solar masses per parsec cubed. But the dark matter density profile is rising, so it's not too surprising that the dark matter density of the solar neighborhood is slightly smaller. So this is just a way to back of the envelope estimate the local dark matter density. In reality, we measure this precisely from various ways, which I'll mention. But you could have guessed within a factor of a few before you even started doing those. Yeah. 10 to 12 solar masses is about the mass of our dark matter halo that we live in. But that extends way out, And I was saying 10 kiloparsecs, so I cut it down by an order of magnitude, using my NFW profile to roughly account for the log that comes from integrating from 10 to the 20 out to farther. OK, and what this means, by the way, is that the dark matter density is roughly going like 1 over r squared locally. And this explains rotation curves. So rotation curves are one of the pieces of evidence for this whole picture, one of many ways that we have to measure this density curve precisely. We have a few different ways to measure our dark matter density profile precisely within the Milky Way. But rotation curves are one of the most powerful, which comes from looking at the rotation speed of stars within our disk, and then inferring the dark matter content and the ordinary content from that. So I think Yonit already went over rotation curves a little bit. So let me just do this quickly. So if you look as a function of distance at the circular speed of matter within the disk, so that circular speed, just saying F equals ma, the mass times the acceleration over r should be equal to Newton's constant, the total mass enclosed within that radius r, and then times that little mass of my test mass over r squared. So that tells me that my circular velocity should be equal to square root of g m over r. So if I had a constant mass within my radius, the circular velocity would be going down like 1 over square root of r as I go farther and farther away. This is a circular velocity, by the way, of things in the disk, because the disk is just co-rotating around. But what we observe is something which actually becomes flat. And what you would expect from, for example, the disk, just the ordinary matter, is you would expect something like this. So this would be just the ordinary matter. Because the ordinary matter, it's not a point mass, so it's not like you expect 1 over square root of r everywhere. But the ordinary matter is confined within the inner few kiloparsec for the most part. So you kind of build that up, and then after some point, you would expect the circular velocity to just start going down like 1 over square root of r. In fact, what we see is it's flat, roughly flat. And so what does this tell us? This tells us that the mass needs to be going like r. So m should be proportional to r. So what does that mean? If m is proportional to r, that means that rho is going like 1 over r squared. Because m is integral d cubed r of 1 over r squared, which goes like r. So this m proportional to r, this flat rotation curve, is actually just a sign that we happen to be living relatively close to the scale radius of that NFW profile. If you study this in more detail, you'll see that by looking out here, you'll see that actually this is going to start to go down a little bit. And it's going to go down because this is going to turn over to 1 over r cubed. And you can also see that as you go in closer, it's going to change to 1 over r. So within the context of this NFW profile, you can use this as a model with free parameters rho 0 and the scale radius, and then fit that model to rotation curve data and measure all these parameters precisely. Yeah?
So if we have really precise rotation curve data, why are there still problems like the forecast problem?
Yeah, so let me mention those problems now, actually. OK, so everything that I've said so far is without baryons. But baryons, ordinary matter, modify things. So how do they modify things? Yeah.
Is there any way like we could have multiple stacks of like baryonic matter within one dark matter halo?
Multiple stacks of ordinary is a question. Are there ways to have multiple stacks of ordinary matter within one dark matter halo?
Because the dark matter is dominant, right? In terms of gravitational dynamics.
Let me answer that question after I draw this picture. So now let's add in baryons. So to first approximation, you would say baryons aren't going to do anything, like what you were just getting at. They're just along for the ride. And that's true, except at the inner parts of dark matter halos. Because remember, the ordinary matter, since it has these dissipative mechanisms and self-interactions, it collapses down to the center of the halos. And the dark matter is fluffy. It remains far away. So even though the dark matter is dominating the mass of the halo, when you get towards the center of the halo, the baryons dominate the potential. So when you get down to the inner few kiloparsec, we're 8 kiloparsec away from the center of the galaxy. When you get down to the inner few kiloparsec, the center of our galaxy becomes dominated by baryons in terms of energy density because they collapse down. So now it's the baryons who are in charge. And the dark matter is along for the ride. That is not true far away, but that is true towards the center of their galaxy. It is the baryons who are deciding what the dark matter does. And so simulations with baryons are hard, but important. And again, baryons in astrophysics includes electrons, in photons. It's just ordinary matter. So there are two things, very broadly speaking, which can happen when you do simulations with baryons, which is what you really should be doing. The reason it's hard, though, to do a simulation with baryons is that baryons are complex. Star formation happens with baryons. So you're never going to simulate that from first principles, where you have every individual baryon, and then they come together and they form a star, and then they go supernova. So you have to do this in some effective way. So simulations with baryons, they put in some knobs. They have some fluid in there for the baryons, with some knobs for things like supernova, star formation, various heating mechanisms. But they're knobs which have to be tuned to data. And so these simulations are really hard to do, but there's been a lot of progress on making them precise recently. And in the context of these simulations, there have been two things have been noticed. One is adiabatic contraction. So adiabatic contraction is the following phenomena. We have our dark matter halo. So here I'm showing the dark matter density as you approach the center of the galaxy. And you start initially with some gas of ordinary matter. And that gas, this is not drawn to scale in the sense that the gas is actually dominating the potential here. So you should, even though I'm drawing the dark matter higher, that doesn't mean anything. The gas is the dominant form of the potential. But the gas can dissipate and can undergo self-interactions, and it's going to slowly collapse down. And as it slowly collapses down, it's going to pull in the dark matter. And so this leads to a more cuspy dark matter profile. So now the baryons are more compact, and as a result, since this happened adiabatically, the dark matter is also more compact. Just one thing to say about this, which I forgot to mention before. The circular velocity also sets the scale for the dark matter velocity dispersion. The dark matter is not just sitting there idly in this halo. It's moving. If it was just sitting there idly, it would just collapse under its own self-gravity, and it would form a black hole, and it would be done with it. So the dark matter is moving with speeds on the order of that circular velocity over there. So if this were to happen not adiabatically, if this were just to crunch down instantaneously, the dark matter, it would not have the right velocity dispersion. It would respond in some weird way. So the adiabatic assumption here means it's happening slower enough that the dark matter velocity dispersion can adjust as this system is collapsing down. But non-adiabatic processes can also play a very important role. And non-adiabatic processes can actually do the opposite. So in addition to adiabatic contraction, there's kind of this cusp versus core phenomena which can emerge. So the second thing which baryons can do is a cusp goes to a core. So above, it was a cusp, which becomes even cuspier. Because a cusp means something that's rising towards the center of the galaxy, and adiabatic contraction makes it rise even more. But you can also have cusps which go to core from non-adiabatic processes. So what's an example of this? Well, let's take the dark matter going up, and then we have our baryon soup here. But let's now imagine there's a non-adiabatic process, which means it happens faster than the dark matter can respond. For example, a supernova goes off, and the supernova injects a whole bunch of energy into this gas, and it just ejects it from the center of the galaxy. So all these baryons just go flying away from things like supernova, or an active galactic nucleus, or some other extreme, which is just a jet around a supermassive black hole, or some other extreme astrophysical phenomena which injects a bunch of energy very suddenly, causes all the ordinary matter to go flying away. So now I mentioned that dark matter has some velocity dispersion, which was set by this potential, and the potential is dominated by baryons. But suddenly that potential is gone, or it's very significantly reduced. The dark matter is moving too fast, and so it's going to dissipate away. And so what this does is it cores out your dark matter halo. So this then goes to, you have less ordinary matter, and you have a cored dark matter halo. So both of these processes, which go in opposite directions, are observed to arise in in-body simulations. And they have different effects and different relative importances depending on which system that you're looking at. So in Milky Way-like galaxies like our own, very recent in-body simulations, just within the past few years, are kind of pushing towards this sorts of phenomena being most important. The idea that at the center of our Milky Way, it's probably contracted and not cored. But still, this is very heavily debated. And the other reason this is debated is because some dark matter models can core out halos, like self-interacting dark matter. But it becomes really difficult to tell if your halo is cored because of self-interactions or if it's cored because of baryons, which we know exist out there in our universe. Yeah?
So with these high energy processes that are flinging baryons out, Would you expect some kind of back reaction from them getting sort of pulled back in?
Yeah, that's a great question. Yeah, do the baryons then kind of get pulled back in? And yeah, they can be pulled back in, and this process can kind of restart, and that chord halo can kind of start to adiabatically become a little bit cuspier. But there are timescales associated with all these processes, and it's a question of what happened most recently. And so at a given snapshot in time, you can observe a chord dark matter halo. It's also possible that ordinary matter, just depending on the size of the galaxy, if it's a smaller galaxy like a dwarf, it could literally be ejected beyond the escape velocity of that halo and it's just gone. So there's no one answer to any question here. It's just kind of, everything you can think could happen does happen in the context of these simulations. Yeah?
I just want to make sure I got the right picture of what you're talking about. So is this like all of the baryons in your galaxy are drawing the pictures here?
Not necessarily. Good. So typically in a typical galaxy like our own, a spiral galaxy, you have the disk, which extends like very far away. We live in the disk, and we're 8 kiloparsec away, and we're not dark matter, we're ordinary matter. So we certainly exist out here. And from rotation curves, you know that there must be matter even farther away from us. But there's more and more dark matter, there's more and more ordinary matter as you approach the center of the galaxy. So within a few kpc, there's the galactic bulge, which is a very dense stellar environment, and it just becomes denser from there on as you go in and in. So within the few inner kiloparsec of our Milky Way, the gravitational potential is dominated by baryons, by ordinary matter.
Sure. I guess it's surprising that like supernova eject enough baryons into the give me a sense of scale.
Yeah, good. So supernova are and active galactic nuclei are very extreme phenomena. These are the units. Well, the units here you kind of need to work them out. But like 10 to the 50 something ergs per second of energy are dumped in from a supernova explosion. And AGN can be even more powerful than that because these are these jets coming off of supermassive black holes. So when you kind of work out the numbers, which is a good exercise to do, to like think about the average kinetic energy in the gas in the Milky Way, because that's what matters is the kinetic energy, and then compare it to the energy injection from a supernova or from an AGN, you'll see that actually these even though it's a single star in the case of a supernova, it's injecting enough energy to really change that kinetic energy distribution of the matter within some surrounding region. And then when you get down to smaller halos, these can be even more important. So when you go down to smaller scales, like dwarf galaxies, supernova feedback is even more important because there's less baryons. On the other hand, the chance of having a supernova is smaller because there's less baryons. So that's why as you go in mass, these different processes become more or less important. And a lot of the anomalies that do exist could potentially be, I think it's fair to say that okay, I'm going to make an extreme statement, but I think it's roughly true. There is not any anomaly in structure formation at present which could not possibly be explained by baryons. But that doesn't mean that it is explained by baryons. It could be that self-interacting dark matter is explaining some of these weird kind of chord halo shapes that we see out there in our galaxy, but it's also possible that it could just be coming from baryons. The reason it's hard to answer that definitively is that there's stochasticity associated with this, and not just like random flips of a coin to whether or not there was a recent supernova. And also, it's hard to do these simulations because you can't simulate from first principles. Okay, so I think I am out of time, which is good timing because let me just tell you where we're going from now. Starting next time, we're going to be focused on now specific dark matter models. Here I've been talking just about in generality about structure formation in dark matter. We're going to take that NFW profile and we're going to combine it with gamma ray telescopes and with WIMP dark matter, in particular some of the better motivated WIMP dark matter candidates like supersymmetric dark matter models such as Higgs-Zenos and WINOs, and we're going to see how we can combine all of these things, and we can go with our gamma ray telescopes and we can look for signatures of dark matter annihilation. But key to doing this is understanding how the dark matter looks in the Milky Way and elsewhere, which is why we started with this explanation. So yeah, I think I'll stop it there, and happy to take more questions. Yeah, in the back.
When you're doing embodied simulation, do you typically reach any
Sorry, can you repeat the question?
Yeah, so when you do n-body simulations, do you typically reach an equilibrium where things are not changing anymore? Or do you have to just stop it at the equilibrium?
Yeah, so the question is, where do you end n-body simulations? Do you end them at the age of the universe, or do you end them at some other time? And yeah, you typically want to go to redshift z equals 0 to today. I mean, nothing ever fully becomes an equilibrium because you still have mergers going on today. So at the end of the day, we are living at a snapshot in time, and the universe is going to continue to do dynamical things from here on out. So it's not like you evolve the simulation until it reaches some sort of equilibrium. You evolve until you get to literally today, and then you end, because we are just living in some snapshot. Yeah, the question is, are these profiles a dynamical thing? And the answer is yes, yeah, certainly. If you were to ask, what is the universe going to look like 20 billion years from now or something, what are the dark matter profiles going to look like? Yeah, things would look different. I mean, you'd have more mergers. You'd have more time for things to virialize. Baryons would undergo more dynamics. We're also in a cosmological constant dominated or dark energy dominated era right now, so things are going to be accelerating more away from each other. So definitely the situation would look very different. Yeah, in the back.
So I have a question which is somewhat related. So it seems to me that this NFW profile is kind of like the sort of equilibrium or sort of background profile, and then you mentioned other structures like subhalos and things like this, which are sort of non-equilibrium. So I guess my question is, what sort of the proportion of the dark matter do you expect to follow these kinds of profiles relative to some other more complicated structures?
Yeah, that's a great question. So the question is, what fraction of the dark matter do you expect to be in this kind of smooth virialized component, and what fraction do you expect to be in some sort of substructure? I don't have the exact numbers off the top of my head, and it's also like a little bit murky, but on how exactly you define these things. But there is kind of an order 1 fraction of dark matter within our own Milky Way halo, for example, which should be in substructure. But it becomes murky on how you even define these things, because if you have a really low mass subhalo, then do you count it as being part of the virialized halo or not? Because those subhalos, to first approximation, are following the NFW profile. So it's like, how do you dissect a halo versus not a halo? And also these halos are becoming virialized. But yeah, to first order, the subhalos themselves are following the same approximation. I say to first order because as you approach the center of the galaxy, they become more easily disrupted. So as you approach the center of the galaxy, you have slightly less than you would expect from NFW. But if you just want to keep a number in the back of your mind, just say an order 1 fraction of the dark matter is in substructure. And this is important for indirect searches because, as we'll see, indirect searches care typically about the dark matter density squared. So if the dark matter is in substructure, you can have a bigger square than if it's not. And so these things, the precise answer to your question does make a difference in the context of indirect searches. Yeah, back.
Complementary to Erwin's question, what is the time that n-body simulations will start with?
Yeah, so what time do embodied simulations typically start with? So you want to start typically after matter radiation equality, but you can do some of that evolution analytically. And then you're in some linear regime, and then you become nonlinear. So redshifts of a few hundred, I guess, it would be a typical time to start running your n-body simulation. Before that, you could do most of the evolution analytically, and then you need to go to numerics. I think we might be out of time because it's lunch, but at least I saw you stand up, so. Hey,
I just want to ask, how frequent is the supernova and AGN energy term? Because
if you want to say something concrete about self-interaction versus this case, we should know how.
Yeah. So it really depends on the system that you're looking at. So
What
for
about the Milky Way? Like, do we have?
yeah, so for the Milky Way, it seems like adiabatic contraction is dominant.
So
but
not
for
that many.
but for subhalos like dwarf galaxies, the more massive dwarf galaxies, it seems like supernova feedback can be very important.
Okay.
But for the low mass dwarf galaxies, it seems like it's not. So it's really a mass dependent question. And then for large clusters, it seems like AGN feedback can be important. So it's really, it depends on mass. Yeah, it depends on the system. Yeah.
Hey, I just wanted to thank you for answering all my questions.
Oh,
I know
yeah,
I asked so many,
no, it's great. It's great. Yeah, it's great. Yeah.
Cool.
Yeah.
Well, thank you. And I'm Catherine, by the way.
Ben, yeah, nice to meet you. Yeah.
Hi.
Hey.
Yeah, I was wondering, like, so for in this in this picture where you have like the cups to core and you eject like different kind of like very high energy particles. So can that somewhat like explain the access for the galaxy center, the gamma ray access?
Good. Yeah. So no, but with one exception, there's a very closely related phenomena to the galactic center access, which is the Fermi bubbles.
Right.
The Fermi bubbles are this extended emission in gamma rays, which are thought to perhaps come from something like AGN feedback, or some previous stage of the supermassive black hole of the Milky Way, where it was active. It had a jet. And that jet did exactly what I described, and is still producing gamma ray emission, but up at high latitudes.
Right, but in this analysis, like the bubbles components are sort of like accounted for.
Yeah, so for the Fermi galactic center access, this can't really do it, but I'm just saying the bubbles themselves are an example of this, which is a similar phenomena, but they did arise from something essentially like baryonic feedback. Most likely, they arose from emission from the black hole of the Milky Way. Yeah.
Thanks.
Yeah.
Also, by the way, I do some like acting on astrophysics.
Oh, cool.
I would like to.
Yeah, that'd be great. Yeah, for sure. Yeah.
Hello, I just
Hi.
have a simple question about
Yeah.
the embodied simulation you mentioned.
Yeah.
So you mentioned that they run over at least several hundreds of redshifts.
Yeah.
So I had a naive understanding that it's very difficult to resolve fixed physical size objects, such as I imagine a dark matter halo.
Yeah.
Across so many number of ethyls.
Yeah.
Because you essentially need a cube enhancement of resolution as the universe expands.
Yeah.
So does the embodied simulation actually is able to do?
Yeah, so a lot of these simulations do zoom-ins. So they start with some very big simulation, they get down, and then they zoom in on some smaller scale, and do it that smaller scale at higher resolution, but using the input from the lower resolution.
I see.
And so you can so these zoom-ins are how we get all of the substructure.
So they do not do a simulation for like a single Hubble patch throughout the.
Not at extremely high resolution.
Right. Okay.
And then they go back to the halo that they care about, and they do that part at higher resolution.
I see. Okay. That makes more sense. Because I was wondering how.
Yeah, I mean, you can do something at very coarse resolution throughout, the entire size you care about, but you only have a fixed amount of memory. So if you want to get to really high resolution, you should go back and do some zoom in.
Okay,
Yeah.
so I guess the kind of similar, not similar, but another big numerical simulation I had in mind is for axion string solutions.
Yeah.
But I guess for there, it's important that you have sort of a volume that's bigger than Hubble at all times.
Yeah. So that's right.
But you're saying for dark matter halo, we can afford zooming in. And
That's right.
Local simulation.
Yeah, it's very hard to do a zoom in on a string simulation, axion string. But for dark matter, I mean, things decouple from the Hubble flow and just become are localized on scales much smaller than Hubble in a way that they're not for axion strings. The strings always extend on the cosmological horizon. Yeah.
That makes sense.
Yeah. Yep.
So
Hey.
I asked you that fuzzy dark matter question
Yeah.
because I'm interested on constraints within like the orbits around.